Hello again. Tonight, the topic is going to be for those of you that haven't noticed it, the universe is active. Things are moving, they're revolving and orbiting, and whole galaxies are moving, and gas clouds are reshaping themselves, but they're so far away and from our perspective, so small, no one ever notices it. For those of you that are amateur astronomers that do imaging, the universe is active. Yeah, okay. The Earth is rotating and going around the sun and all that kind of stuff. But even if you knew that, you may see some things that you hadn't thought of before. And if you're new to the topic, you're not an amateur astronomer that does imaging, you're my target audience for this presentation. You may come away with an epiphany. Hey, the universe is actively moving and zooming, and yeah, golly gee. If you notice the lack of like videos showing this zooming around, it's because when I record the videos with Zoom in the presentation, even if I put animations or videos in the PowerPoint that I'm showing, Zoom doesn't record those when I'm doing like an over the shoulder of the presentation. So, but I do have links that will be included in the YouTube video description that will let you go off and look at them on your own. And I'm working on a couple of different projects. So this may seem like quick filler, which it kind of is because I'm out of time and I haven't finished either of the two. So you may think of things in the solar system and in the galaxy as, sure, they move. You know, you watch the moon changes phases. It goes around the Earth. The same side always faces the Earth. So you might know all that stuff. And as you watch the moon changing over the period of its orbit, you may not be aware of it, but the moon's also out in the daytime sometimes. And doing astronomy public observing sessions, when I would show off the sun in the daytime, people would say, what else can we see in the daytime? The moon. You can't see the moon in the daytime. And I would just point around behind their shoulder because the sun will be here and the moon will be there. And it just dawns on them. The moon's out in the daytime? Yes, it is. In fact, we did that yesterday when we were at the Broward County Central Park, and I noticed where the sun was and the fact that it was just past the summer solstice. So I know the day and night are almost equal in time period. So when I saw the sun, I just pointed over my shoulder and went, the moon ought to be right about there. Turned around and sure enough, the moon's right there. If you know enough about how things move in the universe, you can do a little Kreskin work there. And if you don't know what Kreskin work is, you can look it up. So when you take an astronomical image of something like the nebular cloud in the constellation of Orion, M42, you can even take long duration exposures and stack a bunch of images, getting, hours of image data captured. And when you process it all, it comes out as a static image. Nothing's moving. You could stack those all you want to and show it as a video, and it's still just going to look like a still image. Even as the Earth goes around the sun and we're rotating, you can still take a stack of those images and not seeing anything moving. You can even take images over the course of a year, and you can see that things move in the sky over the course of the year as the Earth goes around the sun, and we watch things move through the ecliptic. But you have to take a lot of different images over a very long period of time, and then you have to do what is known as a blink comparison. You look at one image, you look at another image from, maybe a little less than a year later, and if you put them one on top of the other, you'll see they don't perfectly align up. Even if you take into account the fact that we're going around the sun and the background pattern of galaxies might actually slip a little bit. If you line up on the gas clouds, you can see that they're not perfectly aligned. And that's because the gas clouds are moving. When you look at videos that maybe NASA's got out on the internet, you'll see them taking 3D simulations of the shape of a static gas cloud of the Orion Nebula, and you'll see the camera viewpoint taking a zooming view through the nebula. You can see the dense parts and the hollows and go around newborn stars, but the cloud's not moving. The cloud's static. But in reality, it's dynamic. It's moving. It's a matter of how long you have to take pictures, not how long each picture is, because given the distance, this thing is light years away. Even though it's light years across, the movements are going to be very, very small numbers of pixels over very long periods of time. You can see things moving. To see something that might be moving at thousands of miles per hour over millions of miles over a very long period of time, you have to be really patient, take lots of images, and then make a video of that. I found on the internet. There's a link at the end. There'll be a link in the description on YouTube. The Vela Nebula, which is in the constellation of Cygnus the Swan. The Vela Nebula actually expands and contracts over a long period of time. So it almost looks like the gas and dust of the nebular cloud is breathing. It's not that it just continually expands outward like a planetary nebula might do after a supernova. This is more like the nova's already occurred and you have a nebula and it's just going out and coming back. So the only way we're going to spot all of these sort of either misunderstood, not known that they're there, or not quite fully explained movements is by taking a lot of pictures over a long period of time, not just long exposures, but lots and lots of pictures over years maybe. And then we can actually start to see things moving. And the wide field captures that we're now working into satellites like Euclid and like the Roman Space Telescope that's going to be launched at the end of the month, end of next month, we're going to start to see all of these subtle movements that we either didn't know exist or just kind of, yeah, it's moving, it's taken for granted. We'll actually be able to create videos of things moving because we'll capture enough. The pulse of the breathing of nebular clouds, we don't quite understand where it's coming from, but you can watch the video from the links of the Vela Nebula in Cygnus. And we have to look for more places. So if we want to watch something that's that subtle, we're going to have to watch it from Lagrange point 2 or another Lagrange point, looking out into deep space, taking wide field images over long periods of time. Not long duration captures, but lots of images over a long duration to see things moving. One of the things that as an amateur astronomer is easy enough to spot movement in is Barnard star, which is just a few light years from Earth. And if you take a picture of the background sky where Barnard star is, over a few years, you can actually see that the background sky, if you line up, is the same. But Barnard star is like moving a few pixels at a time, and they have to adjust the baseline coordinates of Barnard star about every decade because it's traversing. It's not just like coming towards us or going away from us. It's actually traveling traverse. So it's moving across our field of view. We need to add more observatories that do these long duration observations to see things. And the more stuff that we get out off the Earth into space with darker skies and bigger apertures, the more that we can start to notice these things. But we have to have the instruments for it too. We need better sensors. We need to start looking in not just visible light or infrared, but gamma, X-ray, the various bands of UV, and then all colors of visible light, more towards the blue, indigo, and violet. And if you knew it or not, the infrared that we look at is not always deep infrared. It's near infrared, which is closer to red. And then slightly beyond that is medium infrared. We don't have that many instruments out there that are getting into deep infrared, which is the next step before microwave radio and then long wave. And we don't have that much going in very long wave or ultra long wave. So we need more sensing at wider spectrum. And in the future, we're going to be looking at gravity waves and neutrinos and things like that. So we want to see everything that's going on and notice movements that we might not have noticed before. Keep looking. So I said it was going to be a short one. So in summary, at a single point in time, things in the universe appear to be static. It's a photograph, it's a still. But as we record things over longer periods of time, we notice that stuff is moving, it's dynamic. You know that the Earth rotates, you know it goes around the sun, and you know that the sun goes around the Milky Way galaxy, but there's more out there moving. The more we look, the more we see what's moving, and the better our sensors are, the more things we'll see that we didn't see before. And so the universe is active. It's alive. And then if you didn't know about, there's some information there. And then down at the bottom, the actual video of the movement of gas, the pulsing of gas in the nebular cloud of the Vela Nebula in Cygnus. Okay, comments, questions?
No, you've explained this before, the Granger point, but I can't remember it.
Lagrange.
Lagrange.
I didn't say it right.
That's okay. Nobody's born knowing any of this stuff, and they keep changing it all the time. Lagrange points, having nothing to do with ZZ Top, because they have a music called Lagrange. which is very nice. So whenever you have a three-body system, like the sun, the earth, and then a point off of that, the gravity is such that it will create points of stability in the gravitational field between these three bodies. The satellite out at Lagrange point 2, which is, if you think of it, sun, earth, moon, beyond the moon, you have L2. It rotates and the earth around the sun. So it's always facing outward. And whenever you hear something is out at L2, that's what it's doing. It's got instruments that are very sensitive to dim light. So it's always going to be pointing away from the sun, earth, moon system out into space. But since it's orbiting the sun with the earth, it's going to be looking at different parts of the background sky over the course of a year.
Right. But what do they mean by the Lagrange point then?
That's what those stable gravity points are. Lagrange was the guy's name. He was the first one that said, I think the gravity might have these null zones, these stability points. And if you were able to put a satellite there, you wouldn't have to expend a lot of your fuel to keep it there. It would be a gravity like null point. And as the Earth swung around the sun, it would just stay in the same spot. The one that's out beyond the sun, earth, moon system is L2. We put a lot of things out there, but not exactly at L2. We create what is known as a virtual orbit about L2. It's not just an orbit about L2 this way. It's actually tilted up. So it's got an inclination to the plane of the solar system. And so that gives it the ability to use moon and earth gravity to kind of like pull it. And so one path of that ellipse, it gets pulled by the earth moon system. So it's a little bit of improvement over just stability, and it can do that part of the elliptical orbit. But then when it has to go back the other way, it needs something to have it push against. The James Webb Space Telescope has this flat plate on the front of the bottom side of the spacecraft, and it uses the solar wind, the particles being emitted by the sun doing their radiation reflection pressure thing, pushing the James Webb Space Telescope the other direction down the ellipse. And then when it goes to the corner of each end of the elliptical orbit is when it has to use a little bit of fuel. It actually rotates the spacecraft using inertial gyroscopes. It rotates it, and then it uses the hydrazine to give it a oomph in that direction or that direction. That's an orbit about L2. There's also two orbits called L4 and L5 that are opposite in the place where the Earth goes around the sun. They're stable there. So we'll tend to put solar observing instruments there because they'll give us two angular views of the sun at the same time. And the NASA stereo solar orbiters were stationed there. And they stayed there for a long time. And then they eventually drifted out, and they would go behind the sun and then come back out again. One of them went behind the sun, and we never heard from it ever again. And the other one went behind the sun and came back out. And so we now have
even a postcard. Wow.
We have one of the two stereo satellites, no longer both of them.
Not even a postcard.
Not even a postcard. No, not even like fan mail from some flounder. That's an old Rocky and Bullwinkle joke.
Having a good time way out here.
Yeah.
Well, thank you for the information.
You're welcome. Any other comments or questions before I stop recording? Okay.